Hello, and welcome back to Boring Sleepy Scientist. Tonight, we're going on a journey. A very, very slow journey. We're going to look at something immense, powerful, and constantly happening, yet so slow most of us never even notice it. We're going to talk about the Earth's tectonic plates. Imagine something as vast as a continent. Now imagine it moving. Not in a sudden, jerky way like a car, but more like a giant, sleepy snail. That's what our Earth does all the time. Continents drift, mountains quietly push themselves up, and our planet reshapes itself. Inch by patient inch, over millions and millions of years. It's a slow dance indeed. So, let's settle in, get comfortable. And let's explore this unhurried ballet beneath our feet here, just as it unfolds across the entire globe. So, what exactly are these plates I keep mentioning? Think of the Earth like an onion, with many layers. At the very top, we have the skin, the very thin outer layer, called the crust. Below that, it gets much, much hotter. We have something called the mantle, which is like a very thick, gooey, almost liquid rock. And even deeper, the superhot core. This layered structure is fundamental to understanding plate tectonics. The core, composed mainly of iron and nickel, is divided into a solid inner core and a liquid outer core, generating Earth's magnetic field. Above the core is the mantle, a thick layer of silicate rock that, despite being solid, behaves like a highly viscous fluid over geological timescales. And finally, the crust, our outermost layer, incredibly thin in comparison to the others, yet the stage for all life as we know it. Now, the Earth's crust isn't one solid piece, like the shell of an egg. Instead, it's broken up into many large pieces like a giant jigsaw puzzle. These pieces are what we call tectonic plates. They're not just the continents we see. They also include the ocean floors, so a plate can have both land and water on it. These plates are not static. They are constantly interacting with one another, driven by forces from within the Earth. The concept of these moving plates revolutionized geology. It's providing a unifying theory for many seemingly disparate phenomena. From the distribution of volcanoes and earthquakes to the formation of continents and ocean basins, it's truly one of the most profound scientific breakthroughs of the 20th century. These plates are incredibly thick, ranging from about 10 to 200 kilometers, or roughly 6 to 125 miles deep. That's like stacking thousands of tall buildings on top of each other. And they're not just floating freely. They're sitting on top of that gooey, moving mantle below. This outer layer of the Earth, the crust, and the very uppermost part of the mantle is collectively known as the lithosphere. It's this rigid, rocky shell that's broken into the tectonic plates we're discussing. The term lithosphere comes from the Greek words lithos, meaning rock, and sphera, meaning sphere, aptly describing this rocky outer shell. Beneath the lithosphere lies the astenosphere, which is the weaker, more ductile part of the upper mantle. It's on this softer, flowing astenosphere that the rigid lithospheric plates actually float and move. The concept isn't that they are floating on water, rather slowly sliding over a semi-fluid layer, much like a thick, cold syrup. This subtle distinction is important because it highlights the mechanical properties of these layers. The lithosphere is brittle and breaks, while the astenosphere deforms and flows. The astenosphere's ability to flow, even if very slowly, is due to the high temperatures and pressures at that depth, which bring the mantle rocks close to their melting point, making them less rigid. It's this continuous, extremely slow deformation within the astenosphere that allows the overlying plates to move. The big question is, why do these enormous pieces of Earth move at all? The answer lies in what's happening underneath them, in the mantle. Remember that gooey hot rock? Well, it's not just sitting still. It's moving very, very slowly. This motion is driven by the internal heat of our planet, a heat that has been present since Earth's formation. Supplemented by the ongoing decay of radioactive elements deep within its interior, this heat is not uniformly distributed. It's hotter, closer to the core, and cooler near the crust, creating a significant temperature gradient. Think of a pot of water boiling on a stove. The water at the bottom gets hot, becomes lighter, and rises to the top. As it reaches the surface, it cools down, becomes heavier, and sinks back down. This continuous circling motion is called a convection current. You can see this phenomenon even in simpler forms, like the gentle rising of heat from a radiator in a room, creating air currents. On Earth, this principle applies to the incredibly viscous, but still fluid-like rock of the mantle. Same thing, but on a much grander and slower scale, is happening inside the Earth's mantle. Heat from the Earth's core rises up through the mantle. As it gets closer to the surface, it spreads out, pushing the tectonic plates along with it. Then, as the mantle rock cools, it sinks back down towards the core, completing the slow cycle. This entire process is driven by the Earth's internal heat, a remnant from its formation, and the decay of radioactive elements within its core and mantle. This immense heat energy is constantly seeking to escape, and convection is the most efficient way for it to do so through the solid but pliable mantle. The difference in temperature, though seemingly small over short distances, creates vast density differences in the mantle rock, driving these powerful, slow currents that have shaped our planet over billions of years. These convection cells are enormous, spanning thousands of kilometers horizontally and vertically within the mantle, taking millions of years to complete a single cycle. It's a grand slow-motion engine driving geological activity. So, these incredibly slow, deep currents in the Earth's mantle are like giant conveyor belts, gently carrying the tectonic plates across the planet's surface. It's this continuous movement that causes all the amazing things we're about to talk about. The average speed of these plates is comparable to the growth of your fingernails, just a few centimeters per year. So slow that if you stood on a plate, you wouldn't feel any movement at all. Yet over geological timescales, these seemingly tiny shifts add up to monumental changes. Imagine moving just 5 centimeters a year. Over 1,000,000 years, that's 50 kilometers. Over 100 million years, it's 5,000 kilometers. Enough to move a continent across an entire ocean. This cumulative effect is truly astonishing, demonstrating the immense power of sustained, consistent force. Even if that force is applied at an almost imperceptible rate, the relentless nature of these movements means that the Earth's surface is constantly being recycled, with old crust being consumed and new crust being generated, maintaining a dynamic equilibrium. Now that we know what plates are and why they move, let's look at how they interact with each other. There are 3 main ways these giant puzzle pieces can meet and move. These interactions at the plate boundaries are where the most dramatic geological events occur. Even if they happen slowly over time, these boundaries are not merely lines on a map. They are zones of intense geological activity, where the raw power of the Earth's interior is expressed on its surface. Understanding these boundary types is key to comprehending the distribution of mountains, volcanoes, and earthquakes across our planet. First, we have what we call a divergent boundary. This is where two plates are moving away from each other. Think of two pieces of a puzzle slowly pulling apart. As they separate, hot, gooey rock from the mantle rises up to fill the gap. This new rock cools and forms new crust. It's like the earth is slowly tearing itself apart at these seams, and new material is constantly welling up from below to fill the void. This process is often called seafloor spreading when it occurs in oceanic crust. As the mantle material rises, the pressure on it decreases, causing it to partially melt, forming magma. This magma then erupts onto the seafloor, solidifying to form new basaltic oceanic crust. This continuous process explains why the youngest rocks on the ocean floor are always found closest to the mid-ocean ridges, becoming progressively older further away. This is happening, for example, in the middle of the Atlantic Ocean. It's creating the Mid-Atlantic Ridge. It's like a giant underwater mountain range where a new ocean floor is constantly being born. It's a very slow process, but it's happening all the time. This vast submarine mountain range extends for about 16,000 kilometers and is one of the most prominent topographical features on Earth. Along this ridge, magma rises from the mantle, solidifies, and adds new material to the oceanic crust on either side, pushing the older crust away. This continuous creation of new crust is what causes the Atlantic Ocean to slowly widen by a few centimeters each year. This seafloor spreading is also associated with hydrothermal vents, unique ecosystems that thrive in the absence of sunlight. Powered by the chemical reactions occurring in the superheated water escaping from the Earth's interior. These vents support diverse communities of organisms, from giant tube worms to specialized bacteria, completely independent of photosynthesis. This constant renewal of the ocean floor means that oceanic crust is typically much younger than continental crust, with the oldest oceanic crust rarely exceeding 200 million years, whereas continental rocks can be billions of years old. Divergent boundaries can also occur on continents, leading to continental rifting, where a continent begins to pull apart. The East African Rift Valley is a prime example, a massive tear in the African continent that could eventually lead to the formation of a new ocean basin, splitting Africa into two smaller continents. This rifting is characterized by volcanism and earthquakes, but on a less intense scale than subduction zones. Next, we have a convergent boundary. This is where two plates are moving towards each other, pushing together. This is where things can get very dramatic, over millions of years. The outcome of a convergent boundary depends heavily on the type of crust involved in the collision. The immense compressive forces at these boundaries lead to significant geological deformation, including mountain building, volcanism, and deep earthquakes. There are a few ways this can happen. An oceanic plate crashes into a continental plate. The oceanic plate will usually slide underneath the continental plate. This is called subduction. It's a very slow descent into the Earth's mantle, where the oceanic crust is eventually recycled and melted back into the mantle. The point where the oceanic plate begins to descend is marked by a deep ocean trench, one of the deepest features on the Earth's surface. As the subducting plate descends, it carries water and other volatile compounds with it. These substances, particularly water, act as a flux, lowering the melting point of the surrounding mantle rock in the overriding plate's wedge. This causes the mantle rock to partially melt and form magma. This magma, being less dense than the surrounding solid rock, slowly rises towards the surface through cracks and weaknesses in the overriding plate, eventually erupting to form volcanoes. This leads to the formation of chains of volcanoes on the overriding continental plate, often parallel to the oceanic trench. A classic example is the Andes Mountains in South America, where the Nazca Plate is subducting beneath the South American plate, creating a long chain of volcanic peaks and frequent powerful earthquakes. The volcanoes in this setting are often highly explosive due to the high silica content of the magma, which makes it viscous and traps gases. If two oceanic plates converge, one will still subduct beneath the other. It's usually the older, colder, and therefore denser one. This process also leads to the formation of volcanoes, but in this case they emerge from the ocean floor, eventually building up to form chains of volcanic islands known as island arcs. The Mariana Islands in the Pacific Ocean, with the deepest ocean trench in the world nearby, are a prime example of an oceanic-oceanic convergent boundary. The Japanese archipelago, the Aleutian Islands, and the Indonesian islands are other prominent examples of volcanic island arcs formed by oceanic-oceanic subduction. These island arcs are typically curved, mirroring the shape of the subducting plate below. The magma generated here often leads to basaltic to andesitic volcanism, which can be both effusive and explosive. If two continental plates crash into each other, neither one wants to sink because they are both relatively light and buoyant. Instead, they are too buoyant to be significantly subducted into the denser mantle. So instead, they buckle and fold, push up huge mountain ranges. Think of pushing two carpets together. They wrinkle and rise in the middle. The immense pressure and compression cause the crust to thicken and deform, leading to extensive folding, faulting, and uplifting of rock layers. The sedimentary rocks that once lay flat on ancient seafloors are squeezed, uplifted, and intensely folded into complex patterns. These folds can be massive, creating wave-like structures hundreds of kilometers across. Visible in the landscape after millions of years of erosion have sculpted them, alongside folding, faulting occurs where rocks break and slide past each other. Thrust faults, in particular, are common in collisional mountain ranges, where large blocks of crust are pushed up and over other blocks, further thickening the crust. The Himalayas, the tallest mountains in the world, were formed this way, and they're still slowly growing. The collision between the Indian plate and the Eurasian plate began roughly 50 million years ago and continues to this day, pushing the peaks higher by a few millimeters each year. This ongoing collision is one of the most dramatic and active examples of continental-continental convergence on Earth, leading to not only the highest mountains, but also frequent powerful earthquakes. The extreme elevation of the Himalayas, reaching over 8,000 meters in many places, is a direct result of this massive crustal shortening and thickening, forming the highest mountain range on Earth. Finally, we have a transform boundary. This is where two plates are sliding past each other, side by side. They're not pulling apart or pushing together, just grinding past each other. This movement doesn't create or destroy crust. Instead, it mostly involves the shearing and fracturing of existing crust. These boundaries are typically characterized by a large number of earthquakes. As the friction between the plates makes the sliding motion irregular, this movement isn't always smooth. Sometimes the plates get stuck for a while, building up a lot of stress. Imagine two giant rough blocks of rock trying to slide past each other. They catch and stick, and the forces continue to push, storing up enormous amounts of elastic energy. Eventually, the friction is overcome, and the stored energy is suddenly released as the blocks slip past one another. When that stress finally releases, it causes an earthquake. The famous San Andreas Fault in California is a transform boundary, where the Pacific Plate is sliding northwest past the North American Plate. This fault system is responsible for many of the earthquakes experienced in California, some of which can be quite powerful as large sections of the fault slip simultaneously, causing widespread shaking. Transform faults are also found connecting segments of mid-ocean ridges, where they accommodate the differential spreading rates along the ridge. These underwater transform faults are also seismically active, though their earthquakes are less likely to be felt by humans unless they are very large. One of the most majestic outcomes of this slow dance is the creation of mountains. We often think of mountains as fixed and unchanging, but they are very much alive, slowly growing and evolving over millions of years. The process of mountain building, or orogenesis, is a profound testament to the immense power of plate tectonics. It's not a single event, but a long, complex process involving multiple geological mechanisms, including folding, faulting, volcanism, and metamorphism, all driven by the relentless movement of tectonic plates. Let's revisit those convergent boundaries, specifically when two continental plates collide. Imagine these two enormous pieces of land, each hundreds of miles thick, slowly, incredibly slowly, pushing against each other. It's like a cosmic wrestling match where the muscles are the forces of the Earth's interior, exerting immense pressure over geological timescales. This isn't a gentle nudge. It's a relentless, sustained compression that lasts for tens of millions of years, building up unimaginable stresses within the Earth's crust. As they push, the immense pressure causes the rocks to buckle, fold, and fracture. Think of pushing a thick rug against a wall. It wrinkles and creates bumps. On a scale of continents, these bumps become mountains. The sedimentary rocks that once lay flat on ancient seafloors are squeezed, uplifted, and intensely folded into complex patterns. These folds can be massive, creating wave-like structures hundreds of kilometers across, visible in the landscape after millions of years of erosion have sculpted them. An anticline forms where the rock layers arch upwards, resembling an inverted U, while a syncline is where they trough downwards, like a U shape. Alongside folding, faulting occurs, where rocks break and slide past each other. Thrust faults, in particular, are common in collisional mountain ranges, where large blocks of crust are pushed up and over other blocks, further thickening the crust and building vertical relief. The repeated thrusting and stacking of rock sheets contribute significantly to the impressive heights of these mountain ranges. The Himalayas, as I mentioned, are a perfect example. The Indian Plate is still steadily crashing into the Eurasian Plate. The Indian Plate began its northward journey after breaking away from the supercontinent, Gondwana, about 140 million years ago, drifting across a vast ancient ocean. It began to collide with Eurasia around 50 million years ago, and that collision continues to this day. This ongoing continental collision is a prime example of how immense geological forces can shape the Earth's surface over vast periods. Every year, the Himalayas get a tiny bit taller, just a few millimeters. But over millions of years, that adds up to towering peaks like Mount Everest. The rate of uplift in some parts of the Himalayas can be as high as 1 centimeter per year, which is a truly remarkable rate in geological terms. This continuous collision is one of the most dramatic and active examples of continental-continental convergence on Earth, leading to not only the highest mountains, but also frequent, powerful earthquakes. The extreme elevation of the Himalayas, reaching over 8,000 meters in many places, is a direct result of this massive crustal shortening and thickening. Furthermore, the intense pressure and heat associated with this collision have caused widespread metamorphism, transforming existing rocks into new types and creating valuable mineral deposits. Other mountain ranges around the world, like the Alps in Europe or the Rockies in North America, were formed by similar painstaking collisions over vast stretches of time. The Alps, for instance, are the result of the African and Eurasian plates colliding over the last 65 million years. A complex process involving multiple phases of folding, faulting, and uplifting. The Appalachian Mountains in eastern North America, though much older and more eroded, are remnants of even earlier continental collisions that occurred hundreds of millions of years ago. When ancient supercontinents like Pangaea were forming, these ancient mountain belts serve as geological records of past plate movements, preserving evidence of long-vanished oceans and continents, providing invaluable insights into Earth's past geological configurations. It's a reminder that even the most solid features of our planet are constantly in motion, sculpted by forces beyond our everyday perception. The very rocks that make up a mountain might have once been sediments at the bottom of an ancient sea, only to be lifted thousands of meters into the sky by the relentless forces of plate tectonics, demonstrating the incredible journey rocks undertake within Earth's dynamic system. So, if plates are always moving, it means continents are always moving too. This idea that continents have slowly drifted across the Earth's surface over vast stretches of time is called continental drift. Sounds like something out of a science fiction movie, but it's very real. The concept was first comprehensively put forward by Alfred Wegener in the early 20th century. He noticed the striking fit of the continents, especially South America and Africa, and observed similarities in fossil records and rock types across now widely separated land masses. However, he couldn't adequately explain how the continents moved, leading to initial skepticism from the scientific community. It wasn't until the theory of plate tectonics emerged in the mid-20th century, providing the crucial mechanism of mantle convection, that continental drift was widely accepted and integrated into the broader theory of plate tectonics. Billions of years ago, the Earth's land masses looked very different. Scientists believe that at several points in Earth's history, all or most of the continents were joined together in one giant supercontinent. These cycles of supercontinent assembly and breakup are a recurring theme in Earth's geological history. Driven by the ongoing processes of plate tectonics, the most famous of these is called Pangaea, which existed about 300 million years ago, during the late Paleozoic and early Mesozoic eras. At that time, what we now know as Africa, South America, Antarctica, Australia, and India were fused together in a southern supercontinent called Gondwana, while North America and Eurasia formed Laurasia to the north. These two vast land masses eventually collided to form the single immense continent of Pangaea, surrounded by a global ocean called Panthalassa. The formation of Pangaea was a monumental event, leading to the creation of vast mountain ranges, and significantly influencing global climate and ocean currents. Over hundreds of millions of years, driven by those slow mantle currents, Pangaea began to break apart. This breakup wasn't instantaneous. It was a slow, gradual process that unfolded over tens of millions of years. Beginning around 200 million years ago, first a rift formed, splitting Pangaea into Laurasia and Gondwana. The Atlantic Ocean began to open as North America and Eurasia moved away from Africa and South America. Then, further rifting caused Gondwana to fragment, with South America and Africa separating from Antarctica, Australia, and India, opening the South Atlantic and Indian Oceans. As these land masses drifted, new oceans formed between them, and existing oceans expanded or contracted. Like pieces of a raft floating away from each other, the continents slowly moved to their present positions. This explains why we find similar fossils of plants and animals on continents that are now thousands of miles apart, like South America and Africa. For example, the fossil of a small freshwater reptile called Mesosaurus has been found in both South America and Africa. This creature, being a freshwater inhabitant, could not have swum across the vast saltwater Atlantic Ocean. So its presence on both continents strongly suggests they were once joined. Similarly, fossils of the fern Glossopteris are found across South America, Africa, India, Australia, and Antarctica, compelling evidence that these land masses were once part of a single, continuous landmass where this plant could thrive. It also explains why rock formations and even mountain chains can be traced across oceans, showing their common origin. For instance, the Appalachian Mountains in eastern North America share geological similarities with mountain ranges in the British Isles and Scandinavia, suggesting they were once part of a continuous mountain belt before the Atlantic Ocean opened up, a testament to ancient continental collisions. Further compelling evidence comes from paleomagnetism, the study of the Earth's ancient magnetic field. As new oceanic crust forms at mid-ocean ridges, magnetic minerals within the solidifying rock align with the Earth's magnetic field at that time, essentially fossilizing the magnetic field's orientation. These magnetic stripes on the seafloor, mirroring each other on either side of the ridge, provide undeniable proof of seafloor spreading and consequently continental drift. The patterns of these magnetic reversals are like a giant barcode on the ocean floor, recording the history of plate movement. Imagine how different the world will look in another 100 million years. The map of our planet is not fixed. Got it? It's a living, breathing, slowly changing canvas. The processes of plate tectonics are not just historical curiosities. They are ongoing, shaping our future landscapes as surely as they shaped the past. The continents we know today are merely snapshots in a much longer, continuous dance across the globe. While most of the time the plates move so slowly, we don't notice. Sometimes their interactions can be more dramatic, leading to events like volcanoes and earthquakes. These are the moments when the Earth reminds us of its immense hidden power, often with sudden and profound consequences. These phenomena are direct consequences of the stresses and releases of energy that occur at plate boundaries, where the Earth's internal forces meet the rigidity of its crust. Let's look at volcanoes first. Many volcanoes form at those convergent boundaries where one plate slides beneath another. This is particularly true for oceanic continental and oceanic convergences. As the oceanic plate dives down into the hot mantle, it's not just passively sinking. It's carrying with it trapped water and other volatile compounds from the ocean floor, as well as hydrated minerals. As the plate descends deeper, the increasing pressure and temperature cause these volatile components to be released into the overlying mantle wedge. This flux melting lowers the melting point of the mantle rock, causing it to partially melt and form magma. This magma, being less dense than the surrounding solid rock, slowly rises towards the surface through cracks and weaknesses in the overriding plate, eventually erupting to form volcanoes. This process is complex, involving the intricate interplay of heat, pressure, and chemical composition. When this magma reaches the surface, it erupts as lava, ash, and gases, creating a volcano. The type of eruption depends on the magma's composition and gas content. Magma rich in silica tends to be more viscous and explosive, leading to violent eruptions of ash, pyroclastic flows, and volcanic bombs. These eruptions can be extremely dangerous, as seen in historical events like the eruption of Mount Vesuvius. In contrast, less viscous magma can flow more freely, forming shield volcanoes with gentler effusive eruptions such as those in Hawaii. This is why we see lines of volcanoes along coastlines, like the Ring of Fire that surrounds the Pacific Ocean. This enormous horseshoe-shaped zone is where a large number of earthquakes and volcanic eruptions occur. It's home to over 75% of the world's active and dormant volcanoes, and is a direct result of multiple oceanic plates subducting beneath surrounding continental and oceanic plates. The Ring of Fire is a stark visual representation of convergent plate boundaries in action, a testament to the immense and continuous recycling of Earth's crust. Other volcanoes, less common but equally significant, can form at divergent boundaries, or even at hotspots, which are areas where plumes of superheated rock rise from deep within the mantle, burning through the overlying plate to create volcanic chains like the Hawaiian Islands, regardless of plate boundaries. These hotspots are thought to be stationary relative to the moving plates, creating a trail of progressively older volcanoes as the plate moves over the plume. Earthquakes, on the other hand, can happen at all three types of plate boundaries, but they are especially common and powerful at transform boundaries and along subduction zones. Remember, when plates slide past each other, they don't always move smoothly. The immense friction between the two grinding plates means that their movement is often jerky and episodic along fault lines, which are fractures in the Earth's crust where rocks on either side have moved relative to each other. Blocks of crust can get locked together. Sometimes the edges of the plates get stuck, like two rough surfaces trying to rub past each other. Think of it like trying to slide a heavy piece of furniture across a carpet. It might stick, then suddenly lurch forward. Pressure builds up over time along these fault lines, immense pressure. As the relentless forces of plate movement continue to push, this stored energy is known as elastic potential energy, analogous to stretching a rubber band. The rocks near the fault deform elastically as this stress accumulates. Eventually, the friction is overcome, and the stored energy is suddenly released as the blocks abruptly slip past one another. This sudden, rapid release of stored elastic energy generates seismic waves that propagate through the earth, causing the ground to shake, which is what we feel as an earthquake. The point within the earth where the rupture originates is called the hypocenter, and the point on the Earth's surface directly above it is the epicenter. Earthquakes vary greatly in intensity, from barely perceptible tremors to devastating quakes that can level cities. The magnitude of an earthquake is measured on the Richter scale, or, more commonly now, the moment magnitude scale. With each whole number increase representing a tenfold increase in the measured amplitude of the seismic waves and about 32 times more energy released. The moment magnitude scale is generally preferred by seismologists, as it more accurately represents the total energy released by large earthquakes. Large earthquakes at convergent boundaries, especially in subduction zones, can also displace vast amounts of ocean water if the seafloor is abruptly uplifted or subsided. This displacement generates tsunamis, giant ocean waves that can travel across entire oceans at tremendous speeds and cause immense destruction upon reaching coastal areas. The Indian Ocean tsunami of 2004, triggered by a massive earthquake off the coast of Sumatra, is a tragic reminder of this destructive potential. Even here, while far from major plate boundaries, the global effects of such powerful events can be felt, emphasizing the interconnectedness of our planet's systems. Earthquakes are a stark reminder of the immense forces constantly at work beneath our feet. They are the Earth's way of releasing the tension built up by its slow, unceasing dance. While they can be destructive, they are a natural and necessary part of the planet's geological processes. Evidence of a living, dynamic Earth. They also provide crucial data for seismologists to study Earth's interior, as seismic waves travel through different layers at different speeds, revealing the structure beneath our feet. So if the plates are always moving, what does that mean for the future of our planet? This means the map of the Earth is never truly finished. It's constantly being redrawn, albeit at an incredibly slow pace. The movement of continents is a continuous process that began billions of years ago and will continue far into the future, creating entirely new geological configurations and reshaping the face of our world in ways we can only begin to imagine. Scientists can make predictions about how the continents might look millions of years from now. These predictions are based on current plate motions, historical patterns of plate movement gleaned from geological records, and sophisticated computer models that simulate geological processes. Taking into account factors like mantle convection patterns and continental buoyancy. While precise predictions are impossible due to the inherent complexity and chaotic nature of some geological systems, general trends can be extrapolated. For example, some models suggest that in about 200 to 250 million years, the continents might once again come together to form another supercontinent, sometimes called Pangaea, Ultimo, or a Messiah. This future supercontinent is envisioned as forming as the Atlantic Ocean continues to widen, pushing the Americas westward until they collide with Asia. Meanwhile, Africa is expected to collide with Europe, closing the Mediterranean Sea, and Australia is predicted to merge with Southeast Asia, further compressing the already complex tectonic zones of that region. Imagine a future where Australia has crashed into Asia, where the Atlantic Ocean is closed up, and North and South America have merged with Africa and Eurasia. It's a mind-boggling thought, and it truly highlights the immense scale of geological time. The landscapes would be vastly different, with new, colossal mountain ranges forming at these colossal collision zones, dwarfing even the Himalayas, and entirely new ocean basins opening up elsewhere as new divergent boundaries form. The distribution of climates would also shift dramatically, as ocean currents and atmospheric circulation patterns would be entirely reconfigured by the new continental arrangement, potentially leading to vast deserts and continental interiors, altered rainfall patterns, and significant changes in global temperatures and biodiversity. The very currents that bring warmth to Europe from the Atlantic would cease to exist, fundamentally altering global weather systems. Of course, these are just predictions, and the exact path of continental drift is complex and subject to change based on the precise forces at play in the mantle and the unpredictable nature of geological events over such long timescales. There are many uncertainties involved in forecasting geological events over such enormous timescales, as small variations in mantle convection or plate interactions could lead to significant divergences in the future arrangement of continents. However, the underlying principle remains. The Earth is dynamic, always changing, always moving. Our planet is a living entity, constantly reshaping itself in its unhurried dance. The slow dance of tectonic plates means that no geological feature, no mountain range, no ocean basin is truly permanent. Everything is transient on the geological timescale, constantly being created, transformed, and eventually recycled. This ongoing transformation is what keeps our planet geologically active and dynamic, preventing it from becoming a static, dead world like Mars, which largely lacks active plate tectonics and has seen its internal heat dissipate much more quickly. The Earth's internal engine continues to churn, ensuring its continued geological vitality. You might be thinking, this all sounds very powerful. Is it something I should be worried about? The answer is, for the most part, no. The movements we've talked about happen over such incredibly long periods that we don't feel them in our daily lives. Earthquakes and volcanoes are the sudden dramatic releases, but the underlying movement is unbelievably slow. For the vast majority of people, the direct movement of plates is imperceptible, affecting them only through the occasional sudden events like earthquakes and volcanic eruptions. Even then, the risks are often localized, and scientific understanding allows for monitoring and preparedness, mitigating some of the dangers. The slow dance of tectonic plates is not a threat. It's the very process that has shaped the beautiful and diverse world we live in. It's created the towering mountains, the deep ocean trenches, and even the very land we stand on. Think about the incredible biodiversity and the variety of landscapes across our planet. From the deep Mariana Trench to the volcanic wonders of Iceland. All of these features and countless more are direct consequences of plate tectonics. The distribution of mineral resources, oil and gas deposits, and even the fertile soils that support agriculture are often linked to past or present plate tectonic activity. Without this slow, unhurried movement, our planet would be a very different place. A geologically dead world, perhaps with a much flatter, less varied surface, and without the constant recycling of crustal materials that provides essential nutrients to ecosystems and regulates atmospheric carbon dioxide levels over long time scales. It's a testament to the Earth's incredible power and patience. It reminds us that there are forces at play on our planet that operate on timescales far beyond human comprehension. It's a quiet, persistent reshaping that has been going on for billions of years and will continue for billions more. This geological rhythm defines our planet, influencing everything from the distribution of continents and oceans to long-term climate patterns, and even the evolution and distribution of life. For instance, the opening and closing of ocean basins can create new pathways for marine life or isolate populations, driving speciation. The uplift of mountain ranges can create new ecological niches and influence regional weather patterns, creating rain shadows and diverse microclimates. Understanding plate tectonics isn't just about rocks and maps. It's about understanding the fundamental processes that govern our living planet, its past, its present, and its deep future. It offers a unique perspective on our place in the universe, reminding us of the immense forces that quietly sculpt the world around us, completely independent of human time frames or concerns. It's a humbling thought, isn't it? The ground beneath our feet, which feels so solid and eternal, is in fact part of a colossal, slow-motion ballet that has been ongoing for eons and will continue long after we are gone. We live on a restless planet, a dynamic system where material is constantly cycled from the interior to the surface and back again. This deep earth process, the movement of tectonic plates, is a fundamental characteristic that sets Earth apart from many other celestial bodies in our solar system. It's a key reason why Earth is so geologically active and, critically, why it supports life. The volcanism associated with plate tectonics releases gases into the atmosphere, contributing to its composition and regulating temperature over geological timescales. The weathering of newly uplifted mountains consumes carbon dioxide, influencing climate. The presence of water and its interaction with the moving plates is also crucial, facilitating melting processes in the mantle and lubricating the subduction zones. So, the intricate dance of these plates is not just about moving land masses. It's about regulating the Earth's climate, creating its diverse landscapes, and ultimately sustaining the very conditions that allow life to flourish. It's a truly magnificent and complex symphony of geological forces, playing out on a stage of unimaginable scale and time. So, as the last remnants of our journey fade, I hope you've gained a new appreciation for the quiet, persistent work happening beneath our feet, right here in Mo'okeker and all over the world. The Earth isn't just a solid, unchanging ball. It's a dynamic, ever-evolving system engaged in a slow, majestic dance that truly defines its character. Take a moment to ponder the vastness of time and the incredible forces at play. It's a lot to take in, but sometimes the most profound ideas are found in the slowest, most unhurried movements. It allows us to step back from our busy lives and consider the deep time of our planet, giving us a sense of perspective on our temporary existence within its grand ongoing story. And perhaps it might even inspire a little more patience in our own lives, knowing that the most significant changes often unfold not in sudden bursts, but through consistent, unhurried effort over time. Thank you for joining me on this sleepy exploration of our planet's tectonic plates. I hope you found it as calming and intriguing as I do. Till next time, remember to stay curious, stay calm, and keep looking at the world with a sense of quiet wonder.